In.bloom was a large immersive space built within a geodesic dome. User interactions manipulated the audiovisual stimulus primarily through the measurement of proximity from hanging robotic objects. These objects, also called blossoms, housed two ultrasonic sensors and would respond to an approaching person by singing out to them via inbuilt speakers and LED strips. To support the resultant melody sung by these blossoms, the entire space was constantly filled by an audiovisual ambience that featured synth drones, repetitive drum loops, and occasional piano chords, each emphasized by an LED animation on the floor. Executing such a multifaceted installation required a networked computing setup, and in.bloom subsequently used two computers, one running Unity 3D, the other Ableton Live 10, and 10 microprocessors, comprising 5 Arduino Unos for the robotic blossoms and 5 Arduino Megas for the LED floor array. Networking these individual processors together was achieved through a combination of serial connections and an Ethernet modem. Considering the inability to arbitrarily set up in.bloom's components, let alone the entire installation, it is difficult to demonstrate how everything works together to produce this infinitely running piece through demo videos alone. This video aims to fill this gap by outlining the connections between each component and exhibiting the musical results. Each robotic blossom leveraged every technical component of in.bloom. The ultrasonic sensors, LED strips, and servo motors were all operated by the embedded Arduino Uno microprocessors, while the audio output was controlled by Ableton Live and sent to the inbuilt speaker via automotive amplifiers. Unity 3D formed as the brain of this operations, and we'll begin with an overview of how Unity 3D managed the inputs and outputs required for each blossom. Unity 3D controlled all aspects of in.bloom. However, it was not responsible for any of the resultant audiovisual content. It simply acted as the conduit between all the other components and performed calculations that would then trigger specific events. In many ways, this setup could have been achieved through Ableton Live alone, especially considering the built-in support for Arduinos via Max for Live, but this chosen setup enabled scalability and performativity if more robotic blossoms were added. Visually, the Unity project features a singular canvas that enables control over all of the parameters of the installation and simply displays incoming and outgoing OSC messages. On the top right corner, OSC messages can be monitored as they are sent and received. These units enable you to monitor different targets if necessary, though in.bloom only targeted Ableton Live 10 computer. The rest of the visual display of the Unity project enables testing of different elements. For example, the Blomprox sliders on the left could test the musical results of a proximity reading for each sensor and was used daily to calibrate the installation. There are numerous numbered buttons on the remaining display that unfortunately illustrate the level of detail not included in the final experience. If you listen to the audio-only version of in.bloom that includes the unused climaxes, you can listen to some of that material that these buttons were meant to trigger. Focusing now on how we communicated with the Arduinos, this project utilized the Arduino asset as available in the asset store. Any Arduino that was connected to the computer via USB would show up in the editor pane on the right and could easily be assigned a unique name that identified that exact microprocessor. Using this asset enabled multi-threading and other advanced features that would have been difficult to pull off with a bespoke system. All of the Arduino communications were then placed on a singular object. This object was called Arduino COM, and it included two components. One, Arduino COM, which was used to talk to the mega Arduinos used for the LED floor array, and the second, Blossom COM, which managed all of the data talking to and from every single robotic Blossom. The script attached to this object defined all of the Blossom objects available in space, and you'll see that we were ready to go up to 10 for the final product, which was the targeted number. The other things that we set up is the LED values, and this will come important in a little bit later because the LED brightness on each object was actually controlled by the volume level of the audio channel output in Ableton. So this script simply set up the Arduino connection using the Arduino manager and would ask it to do essentially two main things. It would ask for the current sensor readings from each Blossom using the send command function, blom1 read sensor, which would ask Blossom1 to please read the sensor. It would then send that data to the audio, and this uses a link to Blom audio component, which we'll talk about in a second, that sends that proximity value along to Ableton. It would then also update the audio level, the LED brightness to be specific, with the incoming Blossom level routing, which we receive from Ableton in a separate component. It would then send this new LED value using a function called blomtrig with the parameter I, which was the new value. It would do this for all objects that were used in the space, and simply the way that Arduino works is that the Arduino would have to check every 15 milliseconds to see exactly what was happening in Unity. Each Blossom had a built-in Arduino microprocessor that self-managed the servo motor position, color saturation of the LEDs, and the ultrasonic sensor readings. To manage all of these aspects, I utilized the NewPing, Servo, Adafruit NeoPixel, and Arduino libraries, as you can see at the top. Of course, I had to define all of the required parameters for those libraries to work. Once we moved down, every time the Arduino was turned on, the serial connection would start up, the servo motor would be initialized, and the initial LED settings would be set. There were two strips of LEDs, as you can see here with the Blom LEDs and the X LEDs. One was housed inside the object itself in a ring around the built-in speaker, while the external LEDs were placed on the outside of the space and lit up so that people from outside could see. Finally, we add the Arduino add commands, and these are the functions that we saw earlier, which are triggered now inside the Arduino. It's a very simple setup. Every loop that the Arduino performs counts the time, and every 15 milliseconds, it updates its Arduino reading. This is because there is no way of talking to Arduino on command, and instead, it constantly listens out for any of those triggered functions. Following that, each sensor reads the closest distance sequentially. After that's done, we correct the default reading of 0 to max distance, and what that means is if there's nothing read, which means there's nothing in the proximity, it equals the maximum distance, which in this case we earlier set to 4 meters. It does that for both sensors, and then checks the sensor proximity values against one another, and makes the new bloom prox, which is the final closest distance measured, to the smallest of those distances. Finally, we set the required sensor position and LED saturation as made by that new bloom prox, and subsequently move the servo into that new position and change the color saturation of both of the LED strips accordingly. Now that happens every loop, but of course that happens regardless of what Arduino says from Unity. So this section here is the bit that is self-maintained, doesn't need Unity at all. And this Arduino update is simply listening out for any of those two functions that could be called. The first of those is bloomtrig. Now, bloomtrig is actually very simple in how it works. All it's really doing is receiving a parameter. In this case, it's the parameter of the volume level of that audio channel. So the trigger is called, we get parameters, and if there is anything stored, update the LED brightness to match. And that just means that if there's no audio level, there'll be no brightness, which means the light will be off. And then the final function that could be called from Unity is the read sensor function, which we mentioned earlier. And confusingly, the read sensor function does not actually get the object to read the sensor, as you saw before. It does that regardless of Unity's need. Instead, this function simply delivers the current closest distance. That's what we call the new bloom prox. And it delivers that back to Unity so that Unity can then tell that to Ableton to manipulate the cutoff frequency. And all it does is a serial.println. This simply sends a value between 200 and 0, which can then be used by Ableton after it's sent through OSE. And that 200 to 0 is just mapped from 0 to max distance. What you'll notice is that the max and mins have swapped. So a 0 in the new bloom prox, which means absolutely touching the sensor, actually equals a value of 200. And the reason we had to switch that is, of course, we want the filter to be at max position when the distance is 0. And we want it to be at 0 when the max distance is reached. The Ableton Live set is organized into 3 main track groups: ambience, blossoms, and climax. Although that last group was unused in the final experience, it can also be experienced in the audio-only mix that includes them. Since we're currently focusing on the blossoms, our attention is going to similarly concentrate on the blossoms track group. Each blossom instrument features 3 devices: the instrument itself, an auto filter, and a Max for Live device that sends the volume level of each of these tracks back to Unity 3D. Each track is associated with a singular blossom, and it has a mono external output. This means that the audio is sent directly to the speaker built into each of these blossoms. If we focus on the cutoff frequency that's in the auto filter, this is the main musical manipulation that these blossoms entail. As a person approaches the blossom, the filter frequency would open. This cutoff frequency manipulation was enabled by the bloom prox in-routing Max for Live device positioned on the OSC routing music track. As Unity sends out the proximity values, they would all come into this singular plugin here. This Max for Live device can look much more complicated than it is once we unpackage all of these embedded objects. But all it does is listen to the OAC messages coming from Unity and then match them accordingly to the correct cutoff frequency, that is, for the correct blossom, and set it to the correct value. So we can see here 2 messages in Max for Live. The input port there, UDP receive, is where the OSC messages come in. And what we see first is the message sent directly from Unity. And you can see a familiar formatting. /blom prox 179. So that means that Blossom 1 has a proximity value of 79. Then I've converted them to appropriate integers that apply to the cutoff frequency to get the exact aesthetic that we're looking for. And I prepend the set value function. So essentially what we've got here is ID 944 is the live object that is associated with the cutoff frequency for object 1. And we have set the value to 55.02, which was converted from the 79. These IDs are an incredibly powerful feature of Ableton, and they were going to be used much more comprehensively when the climax elements were added. They were created using the live.api Explorer application that is available for free download from ableton.com. And this leverages Ableton's creation of a discrete Max for Live ID for any parameter in Ableton once it is targeted within a Max for Live patch. We identified where the cutoff frequency was for Blossom 1, and as soon as we did that, it assigns a unique ID. And once we record that ID, it never changes, so we can absolutely be sure that we're going to be manipulating the exact parameter that we're looking for. And the final device on each Blossom track that completes the circuit of audiovisual stimulus surrounding the robotic blossoms is the Max for Live device called Blom Number Level Out. All this device does on each of the Blossom tracks is read the resultant volume of that track and send that value back to Unity, subsequently manipulating the Blossom's LED brightness. And what that means is that the LEDs will be off unless audio is being emitted. A message would be sent at every 5 decibel difference, and that was just to reduce the numbers that we were getting sent through. in.bloom's ambience layer comprised quadraphonic surround sound and an LED floor array to support the melodies that sang from the blossoms. The setup required for this ambience formed an almost mirrored flow of events to the blossoms. Musical events occurred in the Ableton project, and they would trigger events in the Arduino Megas by sending OSC information back to Unity 3D. We'll begin by exploring the Ableton project and follow the informational transfer as it reaches Unity and finally the Arduino Megas. in.bloom's ambience layer comprises just 4 music tracks: a generative synth drone, repetitive kit, and 1 piano part split into left and right hand variations. The ambience pad track provided the synth drone, and this is perhaps the most important part of this layer. The Appario synth, created by Sugarbytes, is utilized to create this seemingly endless drone. The Appario synth uses frequency modulation and has 16 distinct voices. You can see them in the middle window, each column depicting a single voice. I've leveraged the scale map that you can attach to the pitch shifting function to create a C Lydian pattern that is then arpeggiated between where each of these voices are assigned a different note. You can see the scale in the window below here. It looks like a normal keyboard, except it is relative. So the C that's on this keyboard actually refers to the tonic of whatever note that you press. The arpeggiator that I've used is set up, and basically what it does is it follows the time. So it's set up to the clock, and we've set it to a rate of 1 crotchet, which means every single crotchet the arpeggiator triggers. And the sound is, you can see the arpeggiator cycling through on the top of this middle window, and you'll hear it when we press the button that it triggers a note each time. So to create the variation, of course you can see there's a lot of automated functions in here, but the main ones that I did was using the panning function and also the synth orbit. So heading over to the effects, we'll see that there is a panner function in the middle, and we've put it at full width, which means the synth is actually panning completely from left to right. And you can see there that there's actually 16 individual lines, which means that currently some of the voices are hard left and some of the voices are hard right. I've put it really slow because I didn't want it to be noticeable at all. I just wanted it to morph in a way that created generation. Now, the payoff with that is once you add it to the spatializer, creates a reverb and delay combination kind of sound. Plus the delay and the reverb, what you end up with is a sound that completely moves around the space. So the last way that I use the synth to create generative sounds in this drone is using the orbit function. The orbit mode function of this synth is really unique, and it allows producers to place effect parameters around a graphical user interface and then subsequently orbit around them to create seemingly endless variations within a looped orbital motion. So the red dot that's in the center there, that is essentially where we are currently in the orbit. And I've recorded a very, very, very long loop that just repeats over and over again, which navigates through all these different effects. Right, so what does this actually sound like? Let's have a listen. So as we watch this, it's going towards the arpeggiator and filter. Effect parameters are actually changing the animations according to the position of the orbit as well. Just in case this wasn't enough generative variation, I further obscured the synth's repetitions by using a Max for Live LFO effect to manipulate the synth's position in the quadraphonic sound system. As you can hear, the stereo sound of the synth that we created within Appario itself is constantly changed. We'll only be able to hear outputs 1 and 2 through this output, since it is a stereo output, and you can hear it move between those speakers according to that LFO. The drum kit uses a similar method of creating a generative feel, but this time the Max for Live LFO effects are used to manipulate both the sound's position in space on the surround panner and the cutoff frequency of a low-pass filter. This approach provides an ebb and flow in the kit's presence and provides enough variation while still maintaining the desired meditative aesthetic of the ambience. One aspect of the last two instruments that I skimmed over was their spatialization. In.bloom combines diffusion and surround sound spatialization techniques. The diffusion technique is provided by the inbuilt speakers in each blossom, since their position in the space directly relates to their physical location. But the ambience layer is ethereal, and thus its position is dictated by the positioning the sounds across a quadraphonic setup. Keeping it simple, each ambience track is spatialized using the Surround Panner plugin included with Ableton Live 10. And this device easily enables positioning on the horizontal plane, and as mentioned above, allows the automation of dynamic placement using the LFOs on the track's exact position. So the way this panner was used is that we sent audio signal to 4 separate speakers in a quadraphonic array, And these speakers were corresponding to return tracks, A being for the 1 and 2 speakers, and B being for the 3 and 4. And these were routed directly to the speakers 1, 2, 3, and 4 in the space. These surround panda devices enable the producer to dictate which outputs each speaker is assigned to. And I chose to place each pair of speakers on its own return track, as seen below. This approach enabled control over each pair independently, whilst also easily assigning the discrete external output channel. In some ways, this really was enough work on the surround sound setup. However, I felt a desire for more bass. And realistically, all I wanted to do was build some subwoofers, and this project offered a perfect excuse for such endeavors. And after building the subs and powering them with automotive amplifiers, I decided to create 2 more return tracks that were fed just a portion of this spatialized output. That, if we look at the sense track, we can see I've set C and D. So we have sub 1 on return C and sub 2 on return D. And all we're doing is we're sending the signal from the pair 1 and 2, which has got sub 1 sandwiched between them, and 3 and 4, which has got sub 2 sandwiched between them. And then we're going to filter and gate that information so that all we're left with is the bass. Now we had left and right subwoofer channels, resulting in a 4.2 surround setup, which helped emphasize the spatialization of the sounds, but obviously only delivered the low end. So now that we've got the audio all working through the quadraphonic setup, we have to start talking about how these audio outputs were realized visually. Starting with the subwoofer outputs, it's important to note here that they also triggered unique LED animations that stemmed from the direction of the subwoofer in the space. They would be triggered first on the ambience kit track, which would actually send a message through Max for Live whenever a kick drum was played. This was actually sent through to the patch on the subwoofer output that we're looking at right now, sub 1 OSC out, for example. There's another one for sub 2. This patch would establish the output volume at the time of the kick. It would then filter according to the type of kick sent from the ambience kit track, and it would subsequently send a message onto Unity telling it the type of kick drum, the selected subwoofer, so which side of the space, and the volume of that kick drum at that time. This would then result in an animation triggering on that side of the space that would depend on the kick drum type and output volume. Another main visual feature of the space is actually the periodic large flashes of light that fill the space. These were created as a byproduct of feeling as though the spatialized sound that we currently have from that pad in the kit ran the risk of feeling relatively unstable. So to combat this, I added some full piano chords placed equally in the center of the space, and they emitted equally from all of the speakers. These chords came in fairly sparsely, and they really demarcated the phrase cycles and provided some much needed stability and also some harmonic variation. You can hear them in the background there. Like the kick drum animation triggers, the keyboard part was also triggered an animation in the floor LEDs. This time, to match the fullness of a single instrument playing from all sides, as mentioned before, the LEDs would momentarily flash whenever a keyboard chord was played. And there were 3 chords that triggered these animations: C major, D major, and B minor. And if we look into the Max for Live patch, we don't have to go into too much detail, but you can see there that we've got the MIDI notes according to each of those chords, which make up set 1, set 2, and set 3, each set referring to a single chord. And the set that was played, the chord that was played, I should say, would be sent to Unity using an OSE message that would also include the velocity. Now, the result of this is that the type of chord played would change the color that flashed, and the velocity of that chord would manipulate the brightness of the flash. As I've previously mentioned, Unity provided a channel for information to pass between Ableton and the multiple Arduino microprocessors. For the floor LED array that encompassed the ambience layer, this simply piped incoming OSE messages from the piano chords and kick drums from Ableton to trigger appropriate animations in the Arduino Megas. All the scripts for this pipeline of information were placed on the OSE routing game object, and we'll jump in and look at the sub-trigger routing script first. As the OSE messages for kick drum triggers were received, denoted by a /sub1 or /sub2 string, they were passed for the sub ID, MIDI velocity, and the resultant volume of that subwoofer's output at the time of trigger. The reason behind having both of the velocity and the volume is that a kick drum could have been played with a high velocity, in other words, hard attack or accent, but that the auto filter on that drum set might have had a low cutoff frequency that muffled the output and resulted in a low volume. So, provided the volume was high enough, there we look at sub 1 dB, which is the volume of the track that we've just heard, is greater than min dB, which we can set at any time. Invoke the function sub1trig at 0.5f. And all this does is link to floor, which is the Arduino COM script that we've attached in Unity, and trigger sub1trig. So now let's focus on the Arduino COM script, which takes this information and sends it off to the Arduino Megas. For each subwoofer, the kick drum type would actually dictate hue. The velocity would change the saturation, and the overall volume of the subwoofer would manipulate the value or brightness. So you can see we've set up variables there. And if we head down to the sub1trig function, which is the one that we called before, provided the volume is loud enough, then what you'll notice is that the hue, H sub 1, is set to the sub ID, which means which kick exactly was triggered. Then the S sub 1, the saturation, is associated with the velocity of that kick, and the V sub 1, or value, brightness, is attached to the volume of the subwoofer at the time of triggering. Now, all we basically do is send this onto the Arduinos with an amp_trig function call plus 1, in this case referring to sub 1. These are discrete values in the second variable that describe the exact animation for the Arduinos to trigger. And then the H sub 1, which is the hue, the saturation, and the velocity are sent through. Now, this setup means that every single Arduino Mega will receive this trigger, but each would be programmed individually. Now, the keyboard chord triggers, which we talked about before, is much simpler and it only finishes two variables. One, color choice, which is dictated by the chord played, and two, brightness, which is according to the velocity of those chords. Since it works in exactly the same way as the sub-kick as we've just looked at, I'll move on to the Arduino sketches because this is really where the magic happens. The Arduino Megas single-handedly managed all of the visual content of the ambience layer, which comprised a singular visual array on the floor made out of LEDs, comprising a randomized ambient background, and occasionally triggered extra animations as necessitated by the musical variation. Implementing this proved slightly more difficult than anticipated because it required the utilization of the fast LED library, which enabled multiple layers to a single LED. So in short, I created 3 layers, aptly labeled as LEDs 1, 2, and 3, that corresponded to each of the 300 LEDs in each strip of LEDs in the space. And you'll notice that within this sketch, there are close LEDs and far LEDs. This was required because each Arduino maker could only handle a certain number of LEDs, and it worked out that each Arduino would trigger 2 neighboring lines of LEDs. However, the placement of these lines meant that one side would be closer to sub 1 and the other side would be closer to sub 2. So, the close LEDs would handle all of the sub 1 kick animations and start on the side that the Arduino was sitting on, whereas the far LEDs would be positioned to subwoofer 2 and the animations would start from the complete other side of the space. Every time the Arduino would power on, it would start the serial connection with the PC and add the only Arduino command that we actually used, which was amtrig. And amtrig was used by Unity to simply say, look, there's this extra trigger coming from Ableton, and then the parameters within that function would subsequently be used by Arduinos to determine which animation needed to be triggered. As it moves into the loop function, this is where all of the magic happens. The ambience close and ambience far functions that we see at the start of the loop function essentially just randomized LEDs to become either a shade of a purple or off. So if we scroll down and look at the actual function, it's quite a simple one, but it looked beautiful. And we would randomize the hue between a sort of purpley color. We would randomize the saturation of that color between half opaque to completely opaque. And we would randomize the brightness, anywhere up to relatively bright. We didn't want it to be fully bright because that wouldn't leave us any room for the big keyboard flashes. So after that, we would randomize one LED, which ended up using the purple color, or actually off. The way this works is that it created a slowly evolving twinkle across the floor, as LEDs would randomly come on in an unexpected shade of purple, and then some would turn off. And there was no way of predicting how that would work, so it just created sort of really nice background for everything else to sit on top of. You'll notice that these ambience randomizations occur on the LEDs 3 layer. So there it says close LEDs 3, and in the ambience far it says far LEDs 3. Which meant that whenever the amtrig function was received from Unity, the appropriate animation would actually be triggered on another layer. So if we scroll down to the sub 1 amp kicks, these would be triggered through a switch set, as we say up here. So amtrig would get called, and then depending on the actual parameters, it would trigger either a keyboard flash or it would trigger a amp, an ambient kick animation on either the left or the right side. So if we look at the actual function itself, you'll notice that for the sub 1 amp kick, for example, we're doing a rolling dot of red. So a red LED would go from the edge of the space to the middle of the space. And it's happening on layer 2. What this means is, if we go back to the loop layer, is that at all times, the LED that's actually shown is a blend between those 2 layers. So it's going to be a blend between the purple shown and this subsequent subwoofer kick. Now, when the keyboard chord was triggered, we went down a different path because we wanted it to take over the space and really not be able to see any of the purple. So to get around that, we would simply use the information at hand. So we would say brightness now is 100%, so 255. And the reason for that is we were setting the randomization to anywhere from 0 to about half brightness. And now all of a sudden the space would light up twice as light as it has normally. The second thing we would do is we would use the sort of values of what's sent through Ableton via Unity to dictate the actual saturation of that color. But ultimately, each keyboard key would be sent to a separate function, and we would change the actual color of the flash. The fill solid command, which is built into Fast LED as a library, ensured that all of these LEDs would change to a singular color. This time it was attached to the LED's one layer, and it overrode all of the other blended animations. So basically what we've got here is we've got the brightness going from full brightness, which is 255, eventually to 0 over a number of loops, with each loop reducing by 1. And that would result in an immediate brightness, which would then gradually fade. But because it's on the animation 1 layer, it actually took over the blend that we'd created before. So there was suddenly now no purple, no red dots, nothing, just the one color on every single LED. And then as it faded, what was really amazing is that it had the effect of gradually showing the blend that was about to come. So it wasn't deleting the randomizations that were occurring. It's just that you couldn't see them. And as it came down to nothing, it would slowly, very gradually become purple over time. Well, there you have it. The technical setup of in.bloom leveraged Arduino microprocessors, Unity 3D, and Ableton Live 10 to create robotic blossoms that hung from a geodesic dome and an ambience layer comprising quadraphonic surround sound and an LED floor array. Hopefully, this video has demonstrated how each of these components combine and provides a unique insight into the musical results of the technical setup.